A quick note here about linearization. Now in our control course we will be dealing with linear systems only, but sometimes when deriving equations of motion you will end up with non-linear equation of motion. For example, simply if we have a pendulum, a cart and a pendulum, mass m, length L, and this cart moves horizontally, the motion u. Then the equation of motion of this cart is going to be theta double dot plus g over L sine theta equals u double dot over L cosine theta. Okay. And this is obviously a nonlinear equation of motion. You can derive that simply using the Newtonian or energy approaches. Either way, you will end up with this equation of motion. And I have two nonlinear terms, the sine and cosine. And to get rid of these terms, we're going to use what we know as Taylor series. Taylor series, which says that any function can be approximated as any function f of x is the value of the function at some initial point, reference point x0, plus the time derivative of the function at x0 times x minus x0 plus 1 over 2 factorial the second derivative at x0, x minus x0 squared, and goes on plus 1 over 3 factorial f third derivative x0, x minus x0 power 3, all the way to 1 over n factorial the nth derivative x0, x minus x0 power n. And the more terms you use, the closer the approximation is to the original function. Now, for me, I'm going to need just the linear terms. So I'm going to use just this part of the Taylor series. This is the linear part of the Taylor series because we only have the variable x appearing in the first order. In the second term here we will have x squared, x cubed, and so on. So I'm going to use just this part of the Taylor series. F of x equals f x at 0 plus f prime x at 0, x minus x 0. Now, going back to my sine and cosine here, now I'm gonna try to approximate the function sine of theta equals sine of theta 0 plus the derivative of the sine is cosine theta 0 times theta minus theta 0. So now I need to choose a theta 0. Theta 0 is the point around which we want to linearize our system, which is the point, the middle point of the motion, the neutral point. If the pendulum stops oscillating, the angle theta will be 0. Some applications the angle might be different, but in my case here I will choose theta 0 to be 0. So that makes this approximation sine of 0 plus cosine of 0 theta minus 0 equals sine of 0 is 0, cosine 0 is 1, times theta minus 0 is theta. So the linear approximation of sine theta approximately equals theta, but there's one condition. Since I'm taking just a small part of the whole Taylor series, I would have to put this condition that theta is small. Theta is small. How small is small? In the trigonometric functions, sine and cosine, by trial, you'll find that up to approximately 20 degrees, this approximation is just fine. You can try it, use your calculator, and enter sine of 20. Of course, you'll get a number less than 1 here, but the angle must be in radians. So 20 in radians, the sine of 20 in radians will be approximately the same number as 20 in radians. Then, for the cosine function, cosine theta is cosine theta 0 plus the derivative of the cosine is negative sine theta 0 times theta minus theta 0, which is basically cosine of 0 minus sine of 0 times theta minus 0. Sine of 0 is 0, so this whole thing goes to 0, and cosine of 0 is 1, so that's 1. So cosine theta is approximately 1 for small theta. So my equation of motion now becomes the linear equation of motion theta double dot plus g over L, and sine theta becomes theta equals u double dot divided by L, and cosine theta is 1, and this is my linear equation of motion. And of course I can also find the transfer function s squared theta plus g over L, s squared for second derivative, theta equals 1 over L s squared u, and output theta divided by u is s squared plus g over L, and here we will have 1 over L s squared. And this is my linear transfer function. Input u, the motion of the slider here, and the output theta, the oscillation angle of this pendulum. Of course, this linearization process is not limited to theta equals 0. If in some other applications you find out that the equilibrium position is at some other value, let's say theta equals 1, then all you need to do is substitute 1 instead of 0 in these equations, and you will still end up with a linear approximation of the sine or cosine. And this works also for other nonlinear functions, exponential functions, all other trigonometric functions, and other complexly nonlinear functions.